All right, guys, some more exceptions to the octet rule. It still is a rule. Most of the time, the octet rule is correct. But in some cases, you'll also see an expanded octet, okay, where you'll have more than 8 electrons. And basically, this is where you have a structure where you have no other place to put the electrons. And so this can only happen if it is in the third period or higher. That is, the central atom is in the third period or higher. And so the reason for that is because these atoms in the third period or the fourth period or the fifth period have access to d orbitals. So the d orbitals is actually what's occupying these extra electrons, okay? But that's not too important. You just need to know that if you're in the third period or higher, you could violate the octet rule, but you're only going to violate the octet rule if you have no other choice. And so an example would be bromine pentafluoride here. We have bromine, right? And bromine has 7 valence electrons. So let's write this out. Bromine has 7 valence electrons, and then we have fluorine, which also has 7 valence electrons. It's a halogen, but there's 5 of them. Okay, so 7 plus 7 plus 5, oops, well, that equals 7 times 6, which equals 42. Okay, so if you go through this and you try to put electrons everywhere, you're going to end up with an extra pair of electrons. Okay, basically, I mean, you can look at this. Each fluorine has 2, 4, 6, 8, right? All the fluorines are the same. There's 1, 2, 3, 4, 5 fluorines. So that's 40. And so the 41st and 42nd electron have to go on bromine, the central atom. You're going to want to put on bromine, not on fluorine. You're going to always want to put on the central atom. And if you calculate now bromine, how many electrons it has, as 2, 4, 6, 8, 10, 12 actually in this case. So it really violated the octet rule, but that's the best you can do, okay? Again, not going to be super stable structure. Determine the formal charge. Which structure is the best? Okay, and so we can do this right here. If we calculate this out, we're going to have for oxygen, right? This type of oxygen, all these oxygens are the same. You can see they're all -1, but it's going to be 6 is the number of valence electrons for oxygen minus the 6 non-bonding minus electrons minus the 1 bond. That equals -1. And then for sulfur here, sulfur is also in group 6, and it has 0. It has 0 non-bonding electrons, and it has 4 bonding electrons divided by 4 bonds. 8 bonding electrons divided by 2 is 4. So it's going to be +2. Double check your math here. That should equal 2-. This is a sulfate 2- anion. So, yep, +2, plus and -1, plus and -1, plus and -1, plus and -1 equals -2. And you can go through these and calculate the formal charges for all of these. Okay, this one here is going to be 6 minus 4 minus 2. That gets you 0. And this one is just like this type of oxygen, which was 6 minus 6 minus 1. That gets you -1. And then this sulfur was 6 valence electrons minus 0 minus 6 bonding sites. 2, 4, 5, 6. So that equals 0. And similar sort of logic, I'm sure you guys at this point can calculate the formal charges. If not, you know, consult the previous videos. But you look at this and say, all right, well, this one satisfies the octet rule. Everything looks good. But look here. This one doesn't. Sulfur, you have 2, 4, 6, 8, 10, 12. Again, 12 valence electrons. Expanded octet. But look what happens to the formal charges. More zeros. We have 3 zeros here, right? A 0, a 0, and a 0. And where are the negatives? The negatives are on the oxygens, electronegative atom. That's good. So we have more zeros here. So since sulfur can have those d orbitals, it's in the third row. It can have an expanded octet. It's going to do that. And so this structure is actually going to be a better reflection of reality. Okay. All right. So that's it for this video.